So we don't know what H final is. We can either recognize that it's going to be below this and put in a negative out front, or we can just leave it as a variable, and then when we calculate it, it'll be negative. Now, the other thing that you need to recognize, what should I put for X final? Nope, just Y final. Because this we're saying is 0.15, so then Y final is going to be somewhere down here. But the point is that this H and this X are the same thing for the way we set up the problem. Because the amount the mass goes down is how much the spring is compressed. It's also how much it's moved relative to Earth's gravitational field. So we've got a fun little quadratic that we can punch into our calculators and solve. Then it's compressed 0.209 meters. That must be a long spring, actually. It's compressing 20 centimeters. Anyway, what does the other solution mean? It means it went up. So what would that correspond to physically? When it goes back up, right? So if the mass landed and somehow attached to the spring, then it would go down, and then it would push back up, and then it would eventually come to a stop up here, and it would be this far above that equilibrium length of the spring when that happened. So the correct answer is below the equilibrium point. But if the mass somehow magically attached to the spring, then it would go down, and go back up, and it turns out it would be that far above the equilibrium length of the string. Yeah. But it still has kinetic energy. Like over just the first bounce, like we're assuming that we're not losing any energy to air resistance or heat in the spring or whatever. So gradually it would come to rest and reach the equilibrium position of the mass spring system, which would be halfway between these two values, incidentally. This is not the equilibrium of the mass spring system. This is the equilibrium position of just the spring. So the equilibrium of the mass spring system is going to be below that. But yeah. All right. Here's a fun one. Normal force. What is this shenanigans? Take a moment to read that. In your head, too. Oh, sorry. I dropped my marker. You want that? Yes. Sorry. Oh, I just totally missed it. So, this isn't asking about energy. Uh-oh. What do we do? It's asking about normal force. We should also say this is a circular loop. What? Excuse me. What did you say? Not by definition. Not by definition. So, how do we figure out normal force in this situation? we're going around a, what kind of shape? Circle. So what forces are acting on this car?
Gravity.
And what direction is normal? And
Down.
normal's down. So in the vertical direction we can say what? What can I write here, Andy?
Negative. No.
Mm-hmm. Equals?
This is the last chapter, bro.
Squared over R.
Oh gosh.
And what is R?
R is H over 2.
R is going to be H over 8. So we can say normal force is equal to mv squared over h over 8 minus mg. So we can say normal is mv squared, 8mv squared over h minus mg. Okay, so now we need to figure out the velocity. How do we figure out the velocity?
Top. The velocity is kinetic energy.
Haha. So what kind of energy does the car have initially? How much?
H mg times h.
And what about at the top of the loop?
100
mg times h over 4 and? Right. Mass goes bye-bye. 1 GH minus 1/4 GH gets us 3/4 GH. Multiply that by 2. Gives us 3/2 GH. Well, actually, I'll just leave it like that because our other equation has v squared as well. So then our normal force equals 8m times 3/2 GH over h minus mg. Bye by h. 8 over 2 is 4 times 3 is 12. So it's a good thing that there's friction on roller coasters because otherwise you'd black out. 11 mg is a lot of force. The body can handle like 4 or 5 g's of acceleration. And then you black out because your body isn't strong enough to pump blood up to your brain. Or it's not strong enough to pump blood away from your brain, depending on how your body's oriented. Right, so either way your brain gets deprived of oxygen.
Either way, you're done.
And you black out. Yeah.
Wait, so if you go like really fast,
Not really fast.
car,
If you accelerate really hard, your car doesn't accelerate fast enough to.
What if you? Oh, that's what I always dream when they go.
They have to limit the acceleration of the spacecraft to keep astronauts safe. Well, you start feeling it, like your face is like when you acceleration. Anyway, Atwood's machine. Remember what an Atwood's machine is? It's a pulley with one mass and the 2 masses. Well, my drawing looks like they're going to hit each other, but pretend they don't. And this is the height h above the table. And we want to know what is the speed of the system when m2 hits the table. What kind of energy does the system have initially? Gravitational potential energy. How much? Okay. What about when M2, well, or like the instant just before M2 hits the table? Now, so we do have M1GH, because M1 has now risen that far off of the table. And what else? Kinetic energy. What should I put in for mass? Right, they're both moving. And then we can do a little bit of algebra to solve for V. So this becomes, if I move this over, M2 minus M1 GH times 2 divided by M1 plus M2 square root. Yay, algebra. Okay, for your lab next time, we'll be doing a modified Atwood's machine. I want to do this one last thing before we go. Do you guys know what a pendulum is? So, for a simple pendulum, we assume that our string has negligible mass. Right? So then we just have a mass on the end of a string. The string length is L. And then, it swings up to wherever. Length of the string is still L. And then I'm saying this angle is phi. The Greek letter phi. So, I've heard it pronounced both phi and phi, and both by people with doctorates in mathematics. So, I think it's a potato thing. Potato is a legitimate pronunciation of the word, for the record. Yes. And tomato. Tomato. In Britain, they say tomato. Tomato. Anyway. Yeah, so, what is gravitational potential energy? Right? So this would be our H. So let's do some geometry to find H in terms of L. What can we do? Well, that was quick. If we draw this horizontal, this is the right track. Oh, wasn't the homework already? Oh, my bad. This is phi, which makes this L cosine phi. So then this height is L minus L cosine phi. And then generally it's written with a factored out L. Yeah. And we can do, the reason that I wanted to talk about this is because we can do conservation of energy with a pendulum. The only forces acting on it are gravity and tension. Tension is always perpendicular to its motion, so it does no work, while gravity does work. So, if you're given some initial height, you could find its speed as it passes through its vertical hanging position. Yeah.